Welcome to the second video for Chapter 8. In this second video, we're going to focus on the later half of the chapter, which is all about comparing our sun to other stars. Okay? And if you recall, in the first lecture for this chapter, we talked about the details of our sun. How does it affect this whole solar system? What goes on inside of it? And some key terms for the sun itself. So now let's compare. Okay? All right, so some open questions. How do we measure something called stellar luminosity? How do we measure stellar temperature? It's a great question. And how do we measure stellar mass? These are such intuitive questions, right? How do scientists go about actually doing these things? All right. So the brightness of a star depends both on distance and luminosity. That makes sense. If a star is further away, then it's going to appear less bright, even if that might be a bigger, hotter star, right? Okay. So let's think about how we quantify that. So luminosity is power. It is the actual energy per second, which is measured in watts, the same unit you'd use for the power output of a light bulb or something like that, or a toaster oven, okay? On the other hand, apparent brightness is how it is perceived on Earth. It is the amount of starlight that reaches Earth. So instead of being energy per second, it's energy per second per meter. So we're dividing by another thing. So you can think of Earth as being some area, some cross-sectional area, and the total luminosity is getting spread out over a three-dimensional sphere of energy going out in all directions. And only a really small little piece of that is the area that actually hits Earth. Okay? So obviously apparent brightness is going to be drastically smaller in terms of its actual numerical value than luminosity. Okay? So Alpha Centauri and the sun have about the same luminosity, so the same wattage. Which one appears brighter? Yeah, I bet you know the answer to this one. The sun, of course, because it's so much closer that its apparent brightness is much, much greater. Okay? Now, how does apparent brightness vary with distance? Well, there ends up being a pretty straightforward relationship. It's one you see a lot in science, and it's called the inverse square relationship. Okay? So the amount of luminosity passing through each sphere is the same, okay? Because it's the same energy, and the energy doesn't disappear. It's that whole conservation of energy idea. So if I look at progressively larger spheres, the energy is just more spread out, but it's still the same amount of energy. Now the area of a sphere, the surface area of a sphere, is given by the formula 4 pi r squared, okay? 4 pi radius squared. So what you do is you divide the luminosity, the wattage, by the area, and that's how you get brightness, okay? So then what's happening with that, with the idea then? Well, that means that brightness is decreasing with the square of distance because the surface area of the sphere over which that total energy is spread out over is decreasing. Now you might say, hold on, luminosity is not energy, but it's just energy per time. So as long as the star isn't wildly varying in its power output, then you can kind of hold it steady and say that it's the same amount of energy, okay? So here it is as a formula. Brightness is simply luminosity divided by 4 pi over the distance squared, okay? So that means that you have a unit here, brightness, which is joules per second per area, okay? Like so, right? Because luminosity is joules per second, which is also known as watts, and then here is the area. Okay, so that's it. That's the idea. Now, do you usually want to solve for brightness? Not so much. Brightness is what you measure. What scientists care about, what astronomers care about, is actually solving for the luminosity, which is a property of the star. Okay, and that's a big deal because we want to be able to describe the properties of the stars themselves. We don't care so much how they're perceived on Earth. We actually care about what are they doing. How does one star compare to another? Are there different types of stars? Are there groupings of stars? Are there a normal life cycle of stars? Yes, yes, and yes. So we need to find that true luminosity. I call it the true luminosity because it's a property of the star itself. Okay, so we take the measured brightness here on Earth, and then we need to multiply by 4 pi times the distance squared. Now, how the heck do you know the distance to a star? That's going to be an open question that we're actually not going to address in this chapter, but we very much will address it in later chapters because that's one of the great mysteries and great breakthroughs of astronomy is actually knowing that distance. How far away are other stars? Okay, which is pretty cool. It's not easy to do. It's not trivial. There's lots of different ways it's done. One way leads to another. It's an amazing saga. But for now, let's assume that astronomers have already solved that. We know how far away stars are. Okay? Okay, so how would the apparent brightness of Alpha Centauri change if it were 3 times further away? Think about the formula. Think about how it's proportional to distance. Okay? It's not directly proportional, so we know it's not going to be 1/3. Okay? It's going to be 1/9. Because if you triple the distance, you divide the luminosity or the apparent brightness by 9. Okay? If you quadruple the distance, you divide the apparent brightness by 16 because you just square whatever the distance is. Okay? So how far away are these stars? Okay? So parallax is the apparent shift in position of nearby objects against a background of more distant objects. The apparent positions of the nearest stars shift by about 1 arcsecond. And to give you some perspective, an arcsecond is a really, really small amount of the sky because the sky is divided up into 180 degrees from horizon to horizon if you take a line that goes through the zenith, okay, like the meridian. That's just a line in the local sky, right? A way of dividing up the local sky, your observations of the sky, okay? And so if that's 180 degrees, then every single degree is divided into 60 arc minutes, right? A degree is then, one pretty small segment of the sky. Well, an arc minute's a much smaller segment, but then you can divide arc minutes into arc seconds, and that's what we're talking about. That's a 60th of an arc minute, or a 1/3600th of a degree. Where did I get that number from? It's just 60 squared, because it's 60 per arc minute and 60 arc minutes per degree, right? So 1/3600th of a degree, okay? So the parallax angle depends on distance. Parallax is measured by comparing snapshots taken at different times and measuring the shift in the angle. Can't do it with naked eye observations. It requires actual higher quality telescopes and ideally more sophisticated measuring devices. Okay. This is the idea: is you would do it in July and you would do it in January, and then that angle divided by 2 is the parallax angle. So you could even think of it as being, between March and July, right? Because March would be right here, all right? And so that if you take the measurement in March and then take in July, that would be the parallax angle. Or if you take a measurement in January and then take the measurement in July and divide it by 2, you have the parallax angle. And that divided by 2, you always got to remember it. It's easy to forget. Got to remember it. Because the idea is the parallax angle is part of a right triangle. Okay? It's not a perfect right triangle, but we approximate it as one. And then in doing so, it makes sense, to have that be the angle we're looking at. And then, what are you actually measuring? Well, you're actually measuring this shift, okay? That's the actual shift of the nearby star, the one you can actually measure with this approach, against the background of more distant stars. Because the distant stars remain completely fixed. Notice that the picture of all the white stars are not moving, whereas this purplish star is the only one that's moving, okay? And obviously, it's not going to be as dramatic as that unless the distant stars are really, really distant, okay? So then the parallax angle, right, that angle that is 1/2 of the actual angular shift between a half year, then can be directly related to distance. It ends up being that relationship is in light years 3.26, okay? So in other words, 1 parsec, because that's a unit of distance, a parsec is a unit of distance, is 3.26 light years, okay? That's a bit to take in, I know. A light year is about 9 trillion kilometers, and so that's a really long distance. It's how long it's how long light travels in 1 year. Light's traveling at 300,000 meters per second, right? The fastest thing in the universe. Light can travel really far in short amounts of time. So in a year, obviously, light travels an incredibly long distance, but stars are light years apart. Okay, the distances between stars are unimaginably large. I mean, really, it's hard to comprehend how far apart stars are, okay? And so then the idea is that parallax is even greater than a light year. It's 3.26. Where does that number come from? Just from the idea about that it's 1 arc second. So it's exactly 1 arc second. Here's the kind of conundrum, is there's no star that's actually that close. The closest star to Earth is about 3.5, maybe 3.6, kind of, depending on how you average it out. So let's say it's about 3.6 light years from Earth, right? So, or from the sun. And so that's actually greater than one parsec. So there's no stars that are even 1 parsec away, okay? Now you kind of can round and fudge numbers and say, well, the closest star is Alpha Centauri, Alpha Proxima, which is a 3-star system, by the way, Alpha Centauri A, Alpha Centauri B, and Alpha Proxima. So those stars, you can say, oh, they're about a parsec. And it's kind of a good way to remember it. It's not entirely accurate, but it's close. Okay. So now I did make a big deal saying that we're going to, discuss the whole how do scientists know distance thing later on. Now that's true, but didn't we just discuss distance right now? Yes, but this is just one small part of the story. But it does show you that we can at least know distances. Okay, that for nearby stars we can use this approach. Okay, so this approach is totally valid and useful for nearby stars. Okay. So I want you to kind of take it in to say that, okay, well, that's great. We can actually know how far stars are away as long as they are going to be a few parsecs away, maybe in that, 5 to 50 light year distance. So that's a lot of stars, okay, in our little, wing of the galaxy, our little section of the galaxy on one of the arms, about halfway out from the center. That's great. We can totally do that. We can measure those distances of stars and truly know how far away they are. How? Because of their shift in the sky. Okay? Again, too small to measure the naked eye, totally doable with telescopes. Okay, so now back to luminosity, because at least we have some validity on the idea that we know distances. We can actually quantify distances to nearby stars. All right, so the most luminous stars are about 1 million times brighter than the sun. Okay, these are incredibly huge stars. We're going to see them on a diagram called the HR diagram. Okay, but they're the biggest, brightest stars out there. On the other hand, there's these really, really faint stars, weak stars, barely even qualified as stars, that are about 10,000 times less luminous than the sun. Man, that's not that luminous. I mean, sure, you still wouldn't want to stand on it, it still melts you, but that's not that hot. That's not that luminous. Okay? And an idea is that symbol right there, L subscript sun, that is just the luminosity of the sun. That's the actual wattage of the sun. That would be in joules per second. That's like a giant light bulb. That's how we're thinking about the sun, okay? Okay, so then we have this idea of apparent magnitude and absolute magnitude. Now, why that, right? Why do we, why are we going back to the magnitude scale? Because we made a big deal that we're going to relate luminosity and apparent brightness. Well, there's a thing here, is these numbers. Look at this, look at the difference here, right? That's a huge, huge difference. That means we're talking about stars that are 1 million times brighter and 10,000 times less bright. So the difference between the two is 10 to the 10. 10 to the 10, that's 100 million. Excuse me, that's 10 billion. That's even bigger than 100 million. That's 10 billion, because a billion is 10 to the 9. So that's a 10 billion fold difference between the least bright stars and the brightest stars. So that means that we're going to have a huge difference in terms of how bright they are, let alone the other bright objects in the sky, the planets and the sun itself, and the moon for that matter. So how do we then talk about things that vary in brightness so dramatically in the sky? And you might be like, oh, I look up at the stars. Yeah, they're vary in brightness, but really the only thing that's super bright in the sky is the moon or the sun. Okay, that's true. Okay, but that's for the naked eye. What about the stars that are too faint to see with the naked eye? There's a lot of those. And so astronomers want to quantify those really faint stars that they're picking up with telescopes versus the really bright stars that we can easily see in the sky, like Vega and Betelgeuse and Polaris, these bright stars, and then compare those to Mars and Venus, these planets that are nowhere near as bright as the sun and the moon, but still much brighter than the stars. Okay, so how are they going to do that? They need to use a scale that's appropriate for such a large range of values. And the type of scales, and this is a mathematical reality, that you're going to see in all fields of science that are good for a wide range of numbers are logarithmic scales. Okay, so that's what we're talking about here. Okay, so this is another idea. It's just a reality that we have to have one more rule here, and that's that we're going to relate apparent magnitude to absolute magnitude. Okay, so then let's think about brightness. Okay, so then brightness of a star, the apparent brightness of a star, is then going to be the ratio of those is going to be compared to their apparent magnitude. All right. So essentially, what I'm saying here is that the absolute magnitude is going to be that'll show up here in relation to the luminosity. Okay. But then their apparent magnitude is related to their brightness. But notice in both cases that brightness is a certain value, okay? Brightness you could say, oh, this star is twice as bright as another star. Okay, so that's a number, all right? The units of apparent brightness are, again, going to be joules per second meter squared. There I just took the area that I mentioned before with the A letter and actually split it up into the units of M for meter, all right? So this would be an actual appropriate base units, joules per, and then the whole thing in the denominator, seconds per meter squared. So that's the actual units of brightness, okay? Now, but then what is apparent magnitude? Well, apparent magnitude is not, it's just a number, okay? Because if you think of this as a ratio, and so apparent magnitude has no units. It is unitless. But what it is it's a mathematical convenience, because then we can talk about apparent magnitude, and the apparent magnitudes vary. For the very brightest things in the sky, like the sun, has an apparent magnitude of -27. Whereas the very faintest things in the sky, the things that you definitely cannot see with the naked eye, are going to have an apparent magnitude of like 30. And you might be like, hold on, that's backwards. Why would the positive things be much fainter? Well, that's the nature of having a logarithmic scale. That's the exact same thing with sound. Like if you ever adjusted like a stereo that's measured in decibels, and I don't know if many of you have, but if you have, you're immediately going to recognize what I'm talking about. Because if you turn the sound way up, it starts going into the negative decibels. But if you turn it down, then it's in the positive decibels. So it's the exact same type of logarithmic scale. Decibels are a logarithmic scale, the way sound is measured. Okay? So if that resonated with you, that's great. If you haven't seen stereos that actually have a decibel scale, then you don't know what I'm talking about. Okay? The audiophiles will know what I'm talking about. Okay? So anyway, the apparent magnitude is unitless, and it's going to be based on the exact scale that I mentioned. And that's in reference to a ratio of apparent brightnesses. On the other hand, absolute magnitude, also a logarithmic scale, okay, same exact base here, 10 to the 1/5. 10 to the 1/5 is about 2, okay? And so that same scale is then going to be the ratio of luminosities, okay? All right. So hopefully that will make sense. If it doesn't on first pass, that's fine. You probably need some practice with it, okay? But the idea is these are terms that you need to be familiar with. Apparent magnitude and absolute magnitude, both logarithmic scales. One is related to apparent brightness. The other one is related to luminosity, which, after all, is joules per second instead of joules per second per meter squared. Okay, wonderful. So how do we measure stellar temperatures? Because we're shifting gears now. Up to this point, we did a little foray into justifying that we know distances, but mostly we've been talking about luminosities. Now, it turns out that temperature is another thing, and actually an easier thing, because we don't have to worry so much about the math and the formulas. There's just one simple formula, because it turns out that color is temperature, okay? So, the idea is this. Every object emits something called thermal radiation with a spectrum that depends on its temperature. Okay, and by objects, we're assuming solid objects. This doesn't apply to really low density gases, but it applies great to stars because they're high density. Okay, so object is high density, right? Certainly applies to things like wood, applies to metal, right? So that's the picture here. This is when it's black, its temperature is so low that it doesn't show up in the visible spectrum. So instead, we just see its reflected color, black. But once it starts to glow, it glows red hot. That red then becomes more orange, and eventually it glows white hot, okay? Now the white is just because it's glowing at essentially a peak wavelength of green, which is in the middle of the visible spectrum, so there is as much of the blue light as the red light, so the overlay of those lights are perceived by the human eye as white, okay? But that is definitely hotter than just glowing red. Also, interesting thing, the color of the flames would not apply to thermal radiation. That's a chemical reaction. It is actually an emission of light, and and as such, as a chemical reaction, it is definitely not thermal radiation. But the metal poker here is, okay? So, an object of fixed size grows more luminous as its temperature rises. Hotter objects emit more light per unit area at all frequencies, and hotter objects emit photons with a higher average energy, okay? So direct relationship there between heat and luminosity and heat and particular energy per photon. Well, energy per photon is related to frequency, okay? So it's a fact, energy per photon
is going to be equal to the frequency of the light. It's going to be equal to the frequency of the light times Planck's constant. So it's going to be lambda. Here, I'll just replace the lambda. I'll replace it with F times something called H. We don't really care what H is. It's that Planck's constant word I just mentioned, but we care about that F. So if we could just put it this way, maybe a way that's a little bit more digestible, and just say that the energy per photon is proportional, there's a proportional symbol, all right, to the frequency. So if frequency goes up, energy of the photon goes up. In other words, you can't have high frequency without high energy. High energy photons have higher frequency. What is frequency? It's color, right? Because color is related to the speed of light by this little formula that says the speed of light c is just lambda times frequency. And often when we think about the color of light, we're thinking about lambda. Lambda, by the way, is wavelength, okay? It's the idea that if you think of red light has a particular wavelength. If you think of blue light, it has a different wavelength. Red light is going to be around 550 nanometers. That's short, but that's light. And then blue light, on the other hand, is about 300 nanometers long. They're different length waves, okay? And if you haven't really thought of light as a wave before, this might not really kind of sound like something that makes sense, but that is the nature of light. Light is a wave. It's also a photon, which is a particle. That's often called the duality of light. But not go off on a tangent about the physics of light. The point being is that color is energy, is wavelength, is frequency, which is actually really important because it's simple. Because if you know one, you know all three. If you know the energy of light, then you know its color. If you know its frequency, then you know its energy. If you know its color, then you know its frequency, right? And all together, all at once, all right? So the hottest stars have a temperature of 50,000 Kelvin. Now it's the surface temperature, as we're seeing. We're not talking about the cores. We talked about cores before. We talked about coronas. If you're getting confused with the temperatures, remember the corona of our sun is 1 million Kelvin. Okay, that's because it's incredibly low density, and we don't see that light because it's too low energy, because there's not enough actual particles in the atmosphere, the corona, the upper atmosphere of the sun, to really actually shine. Okay, it's the high density surface that shines, and that's what we see. That's what we're talking about here. These are the surface temperatures. The core temperature is going to be way hotter. Remember, the core of our sun is 10 million Kelvin. The core of other suns is 100 million Kelvin, 10 times hotter. Okay, again, that's not what we're talking about. We're talking about the chromosphere. Okay, the part that we're seeing. All right, the coolest stars are 3,000, and we are not really in the middle. But in terms of actual kind of likelihood of stars, we're a really garden variety, very common type of star, but our temperature is on the lower end, 58 Kelvin, okay? All right, so cool thing about temperature and what's going on with molecules, all right? I'm just gonna run through this because it's a bit of a tangent, but it's relevant. Their level of ionization also reveals a star's temperature, all right? All right, forgot, I was gonna zoom in on this. So when things are solid, all right, then that's lower temperature. As you start to add temperature, they obviously phase change to a liquid. If you continue to heat them up, they eventually break up into a gas, right? Think like water vapor. If you continue to heat them up, then the molecules are going to dissociate. You're not going to have large molecules. For example, if you took water and you continued to add energy to water vapor, eventually the H2O would split up into hydrogen and oxygen, okay? And in fact, the H2 would split up into just H. All right, so that's a molecular dissociation. If you continue to heat it up, now you just have individual atoms at this point because they're so hot, and so that water, as to continue the water analogy, now just individual oxygen and hydrogen atoms bouncing around at high speed. Now these atoms themselves are bouncing around so much they lose their electrons. That's plasma, right? So essentially now the electrons are free. All that's left behind are positively charged nuclei, or just the protons. Okay, and then what happens is then eventually there's full ionization. Okay, there's no leftover electrons. Okay, all right. So that level of ionization tells you something about the temperature. The absorption lines in stars' spectrum tells us its ionization level. So that's actually really important, that there's going to be black lines in certain types of stars. Okay, so this is the first time I'm actually going to sort of pull back the curtain and talk about the types of stars, but this will not be the last. Oh my gosh, not at all. in many of the next few chapters, we're going to talk about types of stars. And if these next few chapters are going to make any sense to you, you have to memorize the types of stars. Okay? There are O, B, A, F, G, K, and M. Okay? Those are the types of stars. And those go from the hottest to the coolest. And furthermore, because there's other types of stars that aren't these types, these are the ones that we're going to start with, and we're going to add a couple more. The ones we add are actually easier to remember. All right, these are the harder ones to remember. Since there are other types, it ends up being very helpful that of these key types, these main sequence types, that's another word I'm going to use a lot, but of these main sequence types of stars, that there are these key absorption lines because they help distinguish the main sequence from the non-main sequence stars. And as we're going to get into that later, especially as we get into the life cycle of stars and the deaths of stars, the geriatric period of stars as they die. And so, that will all make sense, hopefully, as we go on, okay? But for now, we just want to acknowledge that we have these letters and they have absorption lines, all right? One step at a time. By the way, since we're introducing letters, there is a mnemonic device. A mnemonic device, that's the term people use for those like phrases you use to help you remember things. And the one I think it's like modern and clever and easy to remember, is it's only boys accepting feminism get kissed meaningfully. Okay? You can remember that, right? It's going to stick in your mind, okay? And that will order the stars from hottest to coolest. Okay? O, B, A, F, G, K, M. Only boys accepting feminism get kissed meaningfully. All right. So, lines in the star spectrum correspond to a spectral type that reveals its temperature. All right? Okay. So, right? There we go. Yeah. Not a big fan of this one. Okay. No good. All right. So, which kind of star is hottest? Got it? You better got it. Okay. It's A. Okay. Of the four options given here, A is the hottest. Okay. It's the accepting star. All right. So where do these numbers come from? So Annie Jump Cannon was and her associates, basically people who worked under her, were the ones that came up with this naming convention. By the way, back then, since women were not allowed to actually have positions of prestige in universities, pretty awful times. They were called calculators. All right. But yes, that is, yes, it's a terrible term. At the time, these quote-unquote calculators at Harvard laid the foundation of modern stellar classification. Okay, and that's where the letters came from. They didn't know the things that we knew today, but they were, they were classifying them, and they realized that there's different types of stars, but they didn't realize, that they fell in this thing called the main sequence. They didn't realize all the interconnected ideas that followed in the next 100 years. Okay, so how do we measure stellar masses? So far we've got luminosity, we've got temperature, but we still don't have mass. Remember, those were our three questions. Okay, all right. So we can measure mass in a few ways. So the orbits of binary star systems are great ways to measure mass, because as those two stars orbit each other, the actual dynamics, so the Newtonian motion of those stars, are going to tell us about their masses. All right. And there's different types of binary star systems that are going to help reveal masses. There are visual binaries, spectroscopic binaries, and eclipsing binaries. And you might be like, well, but this is only good for binary stars. Well, about half of all stars are binary stars. So that means that we can find stars of basically all the common types that are going to be in binary star systems. Now that means that we're actually in the other half. Our star is not a binary star. That we're not in a two-star system. Okay, it'd be cool to think about what it'd be like to be in a two-star system, but we're not. Okay, all right. So visual binaries are the type where we're looking at the binary star system. So we're looking at the stars orbit each other at like kind of an angle where their orbital plane is perpendicular to our line of sight, and so that's why it's visual, right? So we're actually seeing them orbit around each other. Okay. On the other hand, a spectroscopic binary is where the orbital plane of the two stars that are orbiting each other is lined up with our line of sight. So that means we can't actually see them orbiting each other like this, right? We can't actually see them dancing around each other. Instead, we see one kind of getting pulled on by the other. And so then what we're going to notice is something called the Doppler shift. We're going to, right, and this goes back to, when we talked about exoplanets. This is the same exact technique. And Doppler shift is incredibly sensitive technique because there are certain elements that we know their wavelength very, very well, like hydrogen. And so we can see that shift of hydrogen back and forth. And that tells us the velocity of the star. Once we know the velocity of the star, then we can use Newtonian mechanics to know about the mass of the star, because we can find the gravitational center of mass of that two-star system. Okay? And then eclipsing binaries are great because we can actually look for the periodic eclipse, and we can look for that drop in luminosity, which then tells us the size of the star that's eclipsing the other star. And again, and if all this sounds like similar techniques to how exoplanets are quantified, they are. They're basically the same techniques. Okay? And so direct mass measurements are possible only for stars in binary star systems. And what we need in order to do that is then we need to know the period and the average separation. Essentially, we need to know the radius of their orbit around their collective center of mass. Okay? And so if we know that average separation and we know that period, then we can find the sum of their two masses. Okay? So that's how we measure masses of stars. We need to find some type of star in a binary system. Okay? And so we need 2 out of 3 observables to measure mass. So we either need the orbital period, the separation, essentially the radius, or the orbital velocity. Because if we know the velocity, then we can find R or P. Okay, so the orbital velocity would we get from which type? We get it from the spectroscopic binaries. Okay, and we can definitely get orbital period from any of the eclipsing binaries. And eclipsing binaries sometimes are also spectroscopic. Sometimes spectroscopic are not eclipsing because they're shifted too much, in which case we know we're only getting one component of the velocity. But regardless, we need some combination. It's not perfect. We have to do lots of models here. We have to work with the data that we get. Okay, these are the key ideas in order to measure mass. Okay, all right. So that tells us, through all the incredible amounts of data collection, right? Because it's not like astronomers have only done this for a handful of stars. They've done it for tens of thousands, hundreds of thousands of stars at this point. So we have huge data sets of correlation. And we find that the most massive stars have masses that are about 100 times more massive than the sun, and the least massive ones are about 8% the mass of the sun. That's not nearly as big a difference for luminosity. Remember, luminosity varied from 1,000,000 times brighter to 10,000 times less bright. So obviously, the luminosity varies much more than mass. So in other words, if you have something that's 100 times massive, 100 times more massive, how much more brighter is it? 1,000,000 times brighter. All right. So there's obviously a big difference there. Being more massive means you're going to burn way hotter, and it's not like twice the mass, twice the rate of burning. And of course, I use burning in quotes here. Really, fusion. No, it's like you get you have 10 times, right? Twice the mass, 10 times the rate of fusion. Okay. Okay. So in summary, if we measure a star's apparent brightness and distance, we can compute its luminosity with the inverse square law for light. Right? That was the first idea. We've had so many ideas you may have forgotten already. Parallax tells us distance. Okay, that's one way, but that's an important way. Okay, in fact, it was the first way that we measure distances. Okay, and historically speaking. Furthermore, a star's color and spectral type both reflect its temperature. And then finally, Newton's version of Kepler's third law. And what was that? That was Newton's version of Kepler's third law was the one that was this one: P squared equals 4 pi G over 4 pi times m total times a cubed. Okay, that was Newton's version of Kepler's third law. Okay, a few slides back, like 5 slides back. Tells us the total mass of a binary system if we can measure the orbital period and the average separation. Okay, and then the spectroscopic can help with one of those two, the velocity, the Doppler velocity, or the Doppler shift measured velocity. All right. Okay, so that's great, but we're not done. Now we're going to talk about the patterns of stars. All right, And we're going to get into something called the Hertzsprung-Russell diagram. I mentioned it a couple times. We're finally going to see it, right? And you probably just go like, why do you keep mentioning this thing? Well, now we're going to see it. It's also for short called the HR diagram. Okay, so instead of saying the full name. What is the significance of the main sequence? All right, there's that term again. What are giants, supergiants, and white dwarfs? And why do the properties of some stars vary? Okay, so big questions, big thing about the patterns. Okay, all right, let's get into it. This is it. Okay, and I make a big deal. I'm all excited because this is like the periodic table of astronomy. Okay, it really is. This is the one document of astronomy that you're going to see more than anything else. And if you're going to remember anything when you leave this class, you're going to remember that there is such a thing as the HR diagram. There's one overall figure that is the backbone of all stellar astronomy. And and I say stellar because it's true. This wouldn't apply to studying the solar system and planets, but for any part of astronomy that involves studying stars other than our own sun, this is the key figure. Done. Okay. There's a lot going on it. It has a vertical axis, which is luminosity. Hey, we know what luminosity is. Notice that the units are solar masses. That's nice, actually, because that tells us that one, instead of having it say in watts, one is equal to the luminosity of our sun. So if I draw a horizontal line, I'm going to hit our sun right there. I'm going to circle it so you can kind of think where our sun is. Okay? The horizontal axis is temperature. Okay? Now the horizontal axis is also stellar type, the O, B, A, and so on. All right. Now the weird thing is that temperature gets greater towards the left. Usually axes, numerical axes, they get greater as you move to the right. But notice 3,000 is over here and 30,000 is over here. And again, this is the surface temperature of the star. 50,000 would be the very far extreme, all the way over here. Okay. Remember, because we said that stars can be as hot as 50,000 Kelvin on the surface. I know that's weird, but that's because when they're originally being classified, they didn't know that those temperatures were that way, and they just ordered them from blue to red. Now we know if Annie Jump Cannon had known, I'm sure she would have ordered them differently. Okay, but they didn't. They had no way of knowing what the temperatures were at that time. Okay, so anyway, we've got higher temperatures on the left, lower temperatures on the right, but the horizontal axis is temperature. Okay. And then there's other things you can take from the graph. You can draw these diagonal lines, which represent size. Okay? And so then you can look at stars that fall within a band. For example, all the stars from this one here down to basically our sun fall within 1 solar mass and 10 solar masses. Right? And as they get closer up to that diagonal band, they get closer to the 10 solar mass size. Okay, so size is almost like a third axis, but it's like angled. Okay, and that's the information. All right, the kind of upfront information, the axes and the diagonal line. Okay, now there's more going on because there's the main sequence, which is this band of stars that kind of goes right down the middle, and then there's going to be basically 3 other groups. There's the giants, the supergiants, and the white dwarfs. Those are all ones that aren't main sequence. Okay, yeah, I know it's a lot, but we're going to be seeing it many, many times. Okay, so an HR diagram plots the luminosity and temperature of stars. Yes, it does. Most stars fall somewhere on the main sequence. All right, yeah, you might be like, wait, but the other one had all these other things, the giants and the supergiants. Yeah, but those are not most stars. Those are a tiny fraction, right? Like 99% of stars fall in the main sequence. Furthermore, stars spend 99% of their lives on the main sequence on average. Okay, so the stars that burn really bright and hot, don't spend that much time in the main sequence, but the average star spends a lot of time in the main sequence. Okay. So stars with lower temperature and higher luminosity than main sequence stars must have larger radii. Hence the names giants and supergiants. Okay, that checks out. We'll talk about the actual physical processes that lead the giants and supergiants. Okay, but not now. All right. Stars with higher temperature and lower luminosity than main sequence stars must have smaller radii, hence the name white dwarf. Okay? Okay? Fine. Okay? That's just where these things exist on this particular figure, right? This graph of luminosity versus surface temperature. Okay? So a star's full classification includes spectral type and luminosity. Okay? So spectral type refers to whether you're on the main sequence or not. So the main sequence are type 5, Everything that's not are supergiants, giants, bright giants, and subgiants, giants, bright giants, and supergiants. Notice that that white dwarf isn't even here. So because white dwarfs aren't even actually considered stars, so they actually don't fall. They don't have a luminosity class. All right, they're on the HR diagram. They're important. We're going to talk about them from time to time, but they don't have a luminosity class. All right, so take that for what it is. Okay, and notice that there are more luminosity classes here than we've kind of mentioned so far. I just mentioned supergiants and giants. So bright giants are in between, and then subgiants are less than giants. Okay. Okay. So then, for example, you could have Sirius. That's a well-known star in the sky. It's one you can see with the naked eye very easily, and it would be A1V. Okay. Why is that? Well, because it's got it is an A based on its temperature. It is 1 based on its basically on the absorption lines, and then it's V because it's a main sequence. Okay. All right. So, and I guess you read that as like an A15 because it's a Roman numeral 5. I don't know. So, but it's A1, A1V or A15, however you want to say it. And then the sun is G25, and that's because it's based on its temperature, it's G, based on its absorption lines, it's a 2, and then its main sequence, so it's 5. Okay? Proxima Centauri is another main sequence star. Betelgeuse is not. Okay? Betelgeuse is dying, which means it's not a main sequence star, and that makes it an M2 Roman numeral 1. Okay? So M21. Okay? So the HR diagram depicts temperature, color, spectral type, luminosity, radius. Yes, it does. I think we've established that. All right? So let's do some questions. All right? These are fun. I hope you can follow along with these. I think it'll be engaging. Which star is the hottest? A, B, C, or D? Okay? Make sure you can answer it. It's A. Okay? A is the hottest, right? Because that would be a white dwarf, a particular extreme type of white dwarf. It's got a surface temperature of about 40,000 Kelvin. That's by far the hottest. It's simply just furthest to the right. Okay? All right? Well, misspoke. Furthest to the left. See, even I want to make hot things to the right, but it's not. Hot things are to the left. Okay? Which star is the most luminous? Okay, vertical axis, right? It's C, of course. So that'd be, these supergiants over here are very, very luminous. Now, are they absolutely the most luminous things in the galaxy, or of all stars that exist among all the galaxies? Not really. The most luminous stars are going to be these really, really hot blue stars over here, but the supergiants can get pretty close. In this case, C. We have a C over here. We don't have a letter in this corner. All right, in this corner over here. Which star is a main sequence star? Of the letters showing, A, B, C, or D, which one's the main sequence? You got it? It's D. Okay? And lastly, which star has the largest radius? Okay? All right? Well, it's not the letter that hasn't been used yet. It's C again. All right? B's left out. B just isn't special enough. Okay? So, what is the significance of the main sequence? What does it mean? Okay? Stars spend most of their time there. Most stars are on the main sequence, but it has a real simple definition. It's any star that is fusing hydrogen into helium in its core. Okay? The sun does that. The sun is a main sequence star. Right? We established that based on its luminosity class because it's Roman numeral 5. Okay? So luminous main sequence stars are blue. Less luminous main sequence stars are yellow or red. Okay? So these would be the lowest luminosity, also the longest lived and the lowest mass of the main sequence stars. I say longest lived because notice, right, the lifetime is on here. Right, this particular version of the HR diagram, which is just packed full of information, includes lifetime. These ones live really, really long. Okay, ones like our sun also live long. 10 billion years is nothing to scoff at. But 100 billion years is kind of crazy because these stars here are going to live way longer than the current age of the universe. So we don't even know what the universe is going to be like by the time they die. Okay, all right. So that's it. Mass measurements of main sequence stars show that the hot blue stars are much more massive than the cool red stars. So that's the trend, right? It's not linear, right? But it's definitely kind of it's linear-ish. So kind of a weird curve based on all these complicated physical processes that are occurring. Okay. The mass of a normal hydrogen-burning star determines its luminosity and spectral type. Absolutely. And a normal hydrogen-burning star, that's code for main sequence star. The ones we're showing here. And that's everything that isn't a giant or a white dwarf, right? Okay. So core pressure and temperature of a high mass star need to be larger in order to balance the gravity. So the high core temperature boosts fusion rates, leading to larger luminosities. Okay, because remember the idea of the thermostat that's built into our sun, right? Remember early in this chapter, that applies to all stars, and that means that the stars that are really high mass have to have a different type of thermostat. It's still the same. It's still a thermostat because they still are stable, but that means that they must have much higher luminosity. Okay. All right, so in fact, as we said before, luminosity varies from 1/10,000th as bright as the sun to 1,000,000 times brighter than the sun. The temperature varies from 3,000 to 50,000, it's a good summary, and the mass varies from 8% to 100 times as massive as the sun. There you go. Those are all the stars that exist, okay? All right, summing it all up, okay? So the sun's life expectancy, 10 billion years. Okay, we're not there yet. We're only about halfway through, all right? And that's what's going to happen. Well, that's because the star will, our sun, that is, will run out of hydrogen. Okay? And when it runs out of hydrogen, it's going to start dying. Okay? Now, what about stars that are 10 times as massive as the sun? Okay? Well, they use the hydrogen 10,000 times faster. So that means that they have lifespans of only 10 million years. Okay? Because it's our lifespan times 10, because they have 10 times as much fuel, but since they use it 10,000 times faster, right, these two numbers don't balance out, which means their lifespan is dramatically reduced. Okay? All right. So a star that's just 10 times as massive as our star has a really short lifespan. And that means that a star that is 100 times as massive as our star, well, it would have a lifespan of less than 1,000,000 years. Okay? So, I mean, that's crazy, because, I mean, you think of stars as being, lasting for a long time. 1,000,000 years, that's like, I mean, the dinosaurs are around 65 million years ago. Imagine a star that doesn't even live as long as the time since the dinosaurs roamed Earth. I mean, that is an incredibly unstable star. And there wouldn't even be time for planets to form by the time that star is done. Okay, but those stars do exist. But those stars are important for kind of the propagation of other stars, because they burn so fast that they help spread matter throughout the galaxy. Okay, but they're definitely no good for stable solar systems that could lead to life-sustaining planets. You're only going to find those in the longer-lived stars like ours. But that said, most stars are like our sun. Our sun is the kind of the most common type of star out there. Okay. All right. And then on the other hand, you got these stars that live like 100 billion years, incredibly long. Okay, so high mass stars, in summary, have high luminosity. They're short-lived. They have a large radius, and they're blue. They're blue because the temperature corresponds to a color, in this case, blue. Okay. On the other hand, low mass stars are low luminosity. They're very long-lived. They have small radii, and they're red. Okay, that makes sense. You should memorize that if you can't make the connection. Just straight up memorize it. Okay. So, what are giants, supergiants, and white dwarfs? Okay. So this is just showing how incredibly large they are. Right? This is our sun to scale. It's like 1 pixel, right? And Betelgeuse is that big, and there's even stars bigger than Betelgeuse. It's just incomprehensible how big they are. I mean, like Betelgeuse would like if we replaced the sun with Betelgeuse, it would wipe out Jupiter's orbit. It's that big. Okay. Well, stellar properties depend on both mass and age. Those that have finished burning or fusing hydrogen into helium, well, that means that their cores are no longer on the main sequence. They start to collapse and other things start to happen, right? It turns out that one of the things that starts to happen is they become giants and supergiants. We actually talked about this, right? Because we talked about how our star is going to become a giant because its core is going to collapse. So we've already seen these ideas, okay? So it turns out that this can apply to, all kinds of different collapsing processes. How all those different sublayers of fusion and so on, all right? Now, eventually, after the star burns up all its fuel, leaves behind the planetary nebula, then you can have white dwarfs, okay? All right. So which star is most like our sun? Look at the letters here. These are different letters, right? But which one? Make sure you can answer it. It's B, right? It's actually even covering up, you can see the S for the sun there. Big hint, okay? Which of these stars will have changed the least 10 billion years from now? Okay, it's got to be the longest lived one, right? C. Okay? Which of these stars can be no more than 10 million years old? All right, which one? Which are the ones that burn really, really luminous but have really short lives? A, okay? The big blue main sequence stars, okay? Now, some stars actually vary in brightness. They pulsate, all right? So any star that varies significantly in brightness is called a variable star. Some stars vary in brightness because they cannot achieve a proper balance between power welling up from the core and power radiating from the surface. They have thermostats that don't work very well, right? I mean, they don't just blow up, right? Or they don't just collapse into a black hole or something. So the thermostat still works, but it's pretty janky. Like it's just it's all, so they're always struggling, getting big and bright and then, collapsing in, and they can have this, and it's interesting because a lot of them have these variable properties that happen on a few Earth days. So they're really, it's kind of interesting that the rate is so easy for us to perceive. So such a star alternately expands and contracts, varying in brightness as it tries to find a balance. So here's an example, right? About 50 Earth days between peaks. All right, the light curve of this pulsating variable star shows us that its brightness alternately rises and falls over a 50-day period. All right, so most pulsating stars fall on what's called the instability strip. It's a particular combination of luminosities and temperatures that falls right there. So mostly it's not going to be main sequence stars. It's going to be giants and supergiants. All right, and the most luminous ones are known as Cepheid variables. Okay, why such a weird, far out name? Because they were discovered in the Cepheid constellation, and at the time no one knew what they were, so they were just called Cepheid variables, and the name stuck. Okay, but Cepheid doesn't mean anything other than just a constellation where they were first discovered. Okay, so, and you might wonder, why didn't we even talk about that? It seemed like a weird topic, because it turns out they're super important for measuring distances, but again, more on that in a later chapter. Okay, so in summary, an HR diagram plots stellar luminosity of stars versus surface temperature. Okay, surface temperature is the same as color. If you know color, you know surface temperature. If you know surface temperature, you know color. Okay, what is the significance of the main sequence? Well, that's any star that's fusing hydrogen into helium. That's it, main sequence. Okay. Once you stop fusing hydrogen into helium in your core, you are no longer a star on the main sequence. You're also dying. A star's mass determines its position along the main sequence. High mass, luminous in blue. Low mass, faint in red. Okay, so, all right, there we go. Okay, this is great. I'm glad we've gotten the stars. I love talking about stars, but make sure you kind of brush up on this stuff because it's not like it's going to go away. We're going to be on stars for a few chapters, so it's a good opportunity to make sure you have a good foundation so the future ideas make sense. But regardless, thank you so much for watching this lecture video. I hope it's been interesting, and stay tuned for more to come.